All right, then let's start. Hi, everyone. My name is Max, and I have the pleasure to give a talk about bridging C++ and Python with Nanobind. Just a quick question. Who of you are working with Python? Okay, a few. Are you already bridging C++ and Python, or is this something new? Okay, all right. You know already Nanobind? You know already Nanobind? Or? No, I just okay, then. Okay, let's start. So why there are many motivations to do this. So for me, one of the biggest things is, of course, performance, because C++ offers a huge amount of performance compared to Python, especially in compute-intensive tasks. So it's quite nice. And the other part is basically this combination of productivity. So you can offer a Python interface for C++ libraries, and then you can share it with your colleagues or other people who are not that familiar with C++, and they can basically then leverage whatever you did. Also quite interesting, maybe there is existing C++ libraries, and you want to make it available for people working in Python, or if you want to try something out, you usually do prototyping in Python because it's fast, but then you discover that there are a few issues in speed for certain operations, and then you can easily optimize these bottlenecks in C++. And maybe a bit of history. To my knowledge, the first thing for C++ in this direction was Boost Python in 2002 by Dave Abrahams. Quite long ago, quite powerful, but very complex and heavy, especially back in those days. Package managers like Conan or VC Package were quite rare. So building all up with Boost and Python was quite difficult. And already building the project, I mean, CMake back then was, I don't know, new, quite. Not capable of doing it right. And I tried it once, but it was really a pain to use Boost Python, I have to say. Luckily, in 2016, there was the introduction of PyBind 11 by Wenzel Jakob. From the definitions and syntax, it was inspired by Boost Python, but it was header only, and compared to Boost Python, really lightweight. And it was using C++ 11 and 14, and it's still widely used in many projects, also for big machine learning projects. They offer, like, I think TensorFlow is using or was using PyBind 11, and there are many other examples of it. And then what is Nanobind? It's again by Wenzel Jakob. It's basically a rework or a successor to PyBind 11, which leverages C++ 17 and Python 3.8 and later. And it's compared to PyBind 11, it's smaller, and you have faster compile times due to, first of all, there are less features compared to PyBind 11, because when reading his motivations on his documentation for Nanobind, PyBind 11 somehow grew over the time, and more parties wanted to get some things implemented. And in Nanobind, he's quite strict. It's basically, I would say, a good core to work with, and yeah, it's compiles quite fast. But I have to say, I also used PyBind 11 and never had these big issues with compilation times. But it's quite focused on minimalism, and he's not open to include too much additional dependencies. For example, he rejects to accept pull requests where the algorithm header of STL is included, because in his point of view, this is already huge and not minimalistic enough. So he's quite strict with that. But okay, then let's get started with the first simple example. And those of you who are familiar with PyBind 11, they will recognize that it's pretty similar. Just a few names are different. So basically, you can include Nanobind header, then using the Nanobind namespace, and then you have a simple function add, which you already had in somewhere in your C++ code. So it can be anywhere. You just would need the declaration here. And then you have this NB module part, which is basically a macro which does most of the, or basically the definitions of the things you want to expose in your Python extension. And you have a name, which will be then the library name you have to import in your Python project. And then you have a variable m, which is basically a representation of the module. And then you can simply add multiple things to it. For example, a definition, which is then a function which will be called add. you pass the reference to your add function here, and you can also create a doc string for it, add two numbers. And then compiling everything and setting it up, you can import your extension, my extension, like this name above, and then you can simply call this add function from this extension. You pass in two parameters, 2 and 3, and the result is obviously 5. And there, Nanobind already does quite a lot under the hood, that you can even pass this 2 and 3, and it will be translated to an integer. So the question is, basically, one of the main desires is you want to, of course, exchange data from Python to C++ and back, because otherwise it would be pretty useless. So there are already some automatically conversions between fundamental types like int, float, bool, etc. And there are a lot of things already done for STL containers, STL types. They are basically implemented in Nanobind via a mechanism I will show in a few slides. And so basically most of the STL things just work with the exclusion of an extra header, which is already part of the Nanobind project. And you can, of course, create custom classes, which you can also create bindings for. So this is quite flexible. So, for example, when you want to pass some strings, you simply, you simply basically include the Nanobind STL string header, and then you can write, or you have a function greet, which takes a string by reference and returns a string. And then you define your extension, greet function, and reference to this function, and some doc string. And then you simply call it in your Python world, and then the output is hello world. So, yes?
Well, Python is dynamically typed, so
yes.
On the Python side, what happens if I don't provide a string or something else?
Yes, yeah, good question. We'll come to that, but I can also mention it now. There is the concept of so-called, first of all, there are three ways to exchange data, but one famous one is the so-called typecasting. And Nanobind has, for example, when you include this header, besides the basic type like float, int, etc., where you automatically always have with the Nanobind header the typecasting things, you can register typecasters for string. And what Nanobind is then doing in this generated Python extension, when you look it up, you call your extension function with the string called world, he will try to find if there is any existing typecaster. And in this header, this is defined, and this is in the end, you will see in a moment, it's a template specialization on this type. And this can basically, Nanobind walks all of these typecasters which are registered, so basically over all template specializations. And if one of them accepts it, basically, then he will use this typecasting functionality. Clear, someone? Then you will get a runtime error, and instead of here, there will be could not match anything, and then he lists the functions with the same name. And if you have multiples with different arguments, he will list all the possibilities and say could not match your arguments to the ones provided in the extension. The microphone. Yeah, maybe pass it over for recording the questions. All right. And this also works with lists. So basically, when you have the kind of analog to Python lists with somehow an STL vector. So when you have a vector, which basically a function which sums it up, and it's a vector of integer, just sums it up, and then you bind it, as in the previous examples, and then you can call this with a list. All right? This works, and the list gets converted to an STL vector. But anyone expecting some downsides here, maybe?
Could be an array.
Could be an array, yes. But generally, this list, there is no direct representation in the standard template library of a Python list. So basically, there has to be a copy of the data to get it into a vector. And this is one of the downsides with this built-in typecaster. So basically, when you pass a Python list to C++ function, which expects the vector, the underlying data will be copied, because the list representation of these Python objects is not somehow working with how the memory data layout of a std vector is. Okay? For small things, it's not a big deal. Yes?
Is there a representation of a Python list in Nanobind, so I have
Yes.
some custom. Okay,
It is.
that would be the more efficient way.
There are even more efficient ways. So.
What about strings? Would strings be copied or not?
To be honest, now I don't know by heart. I would say that my guess would be that they can extract the string from the underlying Python object, but I'm not 100% sure, to be honest. Most likely also copied into the STL. Copied. No, I correct myself. It will be pretty sure it's copied. But they have also a representation. There's also a typecaster for string view, and I would hope that the string view then can somehow take advantage of the underlying string buffer in Python. But the STL string has to be copied, pretty sure. And okay, for large data sets, this can be, of course, inefficient. So, I mean, as I said, for small items, you don't recognize it, but if you start with a list of 1 million items and you do it constantly, will not work that good, I guess. And you also have to note that this happens in both directions. So when you plug a list into a function in C++ taking a vector, it will be copied. And when you have a function returning a vector, this will be then converted to a list and there's another copy. So you have it on both directions, basically. But usually when you work in Python with large lists, you also usually don't work with 100 million items lists in Python, but you maybe use Eigen or Numpy. I guess most Python users are already aware of Numpy, I guess. You're not? You're looking skeptical?
I'm not a Python user.
Okay, sorry. But okay, then for the audience who are not aware of Python, Numpy is basically the vector and matrix standard or one of those standards in Python. Basically, the data structure is a Python wrapper around C data structures. So basically, they created, not with Nanobind, but with their own infrastructure, bindings for a C library. And it can handle basically most of these linear algebra operations. And the nice thing with this, since this is already some memory buffer in C, you can provide zero-copy typecasters. And the Nanobind library is already doing this for you, for this Eigen and Numpy stuff. So basically, with this, you just get in the typecaster access to the underlying memory buffer of the Numpy array or the Eigen data structure, and it can be simply mapped over into the C++ world, which makes it very efficient, especially when you work with large data, then you don't have to copy anything. So, for example, how does this look like? Of course, there is a separate header for the Numpy ND array, which is then a separate type in Nanobind. ND array, and you can specify it with float, and if the storage is continuous, and then you can simply, once this header is included, you can simply pass Numpy arrays into your function. And then the underlying data or buffer is not copied, so this is quite efficient. And the same works for Eigen, and yeah, not much to do on this side. Okay, then back to your original question. So what are typecasters? So typecasters are basically the method Nanobind, or one of the methods Nanobind used to transfer data between Python and C++. As mentioned, they have for built-in types, SQL containers, Eigen and Numpy arrays, you already have it. But you can also write your own typecasters for your own classes or types. And how this looks like. So for example, assume you have a simple struct which just holds one integer value, and you want to exchange instances of this struct back and forth between Python and C++. All right? Any questions? Sorry. No. Then the interface you basically have to implement, you have to make a template specialization for the Nanobind typecaster struct based on your type. And then you have to do one macro line with your struct and you name it, which is then basically the Python name of your thingy. And this macro defines also a member in this struct, which is called value. And then, since you have two directions from Python to C++ and from C++ to Python, you basically have to implement how these transformations should be handled. And for example, we have a struct which has one member called value, which is an integer. So when we are coming from Python, you get basically a source handle, and you have other options, which is that you can specify advanced policies on lifetime, etc. But I skipped it for this presentation. So when you got a so-called source handle, you have to check if it's an instance of an integer. Because if it's something else, for example, a string, then this typecaster is not appropriate, because when you pass in a string, how you should convert it to a struct which holds one integer. So this will not work. So basically, or most likely, this is not what you want. So basically, you check if the thing passed in is an integer. If it's not, you simply return false, and Nanobind goes to the next possible list in the typecasters. All right? And if you stay here, you safely can cast this handle to an integer, and since this macro above defined a member value, which is of type myStruct, it's a bit unfortunate here, but you have then value.value, and you can assign the integer to it. So basically, you take an integer from Python, and this typecaster in the one direction simply writes it to the value. And the other direction from C++ to Python, so you get a simple struct, then you take the value, convert it to an int, and the release converts this value to a handle, and this is the thing Nanobind can give back to Python. So this is pretty straightforward. I mean, of course, if you want to work like Nanobind does with Numpy arrays, you have to do a lot of more work to safely access the underlying memory buffer. But there are a lot of examples in the library how you do it. And basically, you have to implement, specialize this template, and then implement these two functions. And of course, yeah, working with memory buffers in a safe way is tricky always, but yeah. All right. There is also another way Nanobind offers you to transfer data. It's called the bindings option. There you simply can say, I mean, there's also a lot of magic going on in this bind vector function, but you can say you have a vector of integer, and then you create bindings for it, and then it doesn't do the conversion to lists, but it rather keeps the type. So you have then an extension type of int vector with a certain value, and then you can also program operations on this. And there's also a third one, which is then basically the thing you asked, but I didn't mention on the slides. This is called wrapping. So you can also access in the C++ code directly a Python object. The Nanobind has something for it called Nanobind list. And then you can simply work basically with the Python object representation. But this has to be then crafted for every Python object you want to do. And from my experience, basically for the types you want to do it, for these basic types, it's already done in Nanobind. And usually, I never did a wrapper on my own. All right. But Nanobind also has more to offer. You can also bind complete classes with constructors and methods, etc. Imagine you have a simple class point consisting of two floats, x and y, and you have a norm function which simply calculates the Euclidean norm and two members, x and y. And then you can say, okay, I have my class, it can be anything, and you can then make in your module an nb class underscore binding for the whole class of type point in your module m, should be named point, and then you can define on this class definition a bunch of items. For example, the constructors are marked with Nanobind init, and then you simply pass in the types you want. And then Nanobind, when it sees you construct this object in Python, searches all these constructors you made available according to the argument you passed in. And also quite nice, I didn't mention, but you could also define here lambda functions. So if you want to do a little bit more, if you have a third-party C++ library you want to map, but you cannot directly map it, you can here simply write lambda functions and the bindings just work, which is also quite nice. And you can have multiple constructors if the types are different, of course. And so basically then we can forward or bind the norm function, and we can bind x and y as members, or as the fields. And so basically in Python we would import it, then we would simply create the point class with 3 and 4. We can call our norm method, and we can also access the fields. Yes? Maybe the microphone, sorry.
The RW, I guess, stands for right?
Yes. Also, it's on the next slide. No problem. But so basically what you can do with classes, so you can bind constructors with this definition and then this init tag. You can bind methods just with def. Then you can access fields, so basically the member variables in your struct with def RO for read-only and def RW for read and write. Then you can also write getters and setters with this def property read-only, read-only, read and write. Then you can also define static methods, and the same for static fields and properties. So these are everything you can bind with for classes. There are also possibilities to bind enums, etc., but I didn't mention it. You can find it then on the very well documented Nanobind class. All right. Another thing, so now we are done with the basics, but often you don't work with a single NumPy vector or whatever. Many applications require some things like a data frame where you basically have a table or something, or a two-dimensional set of data. And the question is how you can pass over this. I mean, I guess most of the Python users ever heard of Pandas, I guess, and Polars maybe, yes, and Apache Arrow. Apache Arrow is basically a so-called columnar data memory format where they spend a lot of development and design on how you efficiently on modern CPUs can store data. They have a few concepts like an array, which is basically when you consider it's a polymorphic type, which have different realizations for double. For example, a double array can consist of a continuous array of doubles. Then these Apache arrays have the feature that every type is every array can have nullable elements, so they store additionally to the data, which represents in this case the double vector, a bit mask saying which fields are even set or which are null, which is compared to NumPy a huge benefit, because in NumPy it is only possible for floating point types where they use basically none to represent it, but when you have an integer and you join it and then you get a none, it automatically converts it to a float column, because integer NumPy arrays cannot represent missing values. So this is one of the key benefits of Arrow. They have concise definitions for everything. Everything is nullable. Then they have the concept of chunked array. This is basically a list of arrays. So the idea is when you have really huge data sets, you may not easily find enough continuous memory space. This is then maybe problematic. So you can chunk your huge data into a list of arrays, basically, where each of the items is then continuous. And the analogon is then the table and the record batch. So basically the record batch is a set of columns or a set of arrays, basically, and you can define a schema definition, etc., where you can say this column has this name and is exactly of this type. And the table is basically consists of chunked arrays. So that's, I mean, I don't know if it was too fast, but I can also explain it later. Then PyArrow is the default backend for Polars, so this makes it then quite tempting to use Polars in Python and then easily transform the underlying Arrow table directly to Nanobind, or via Nanobind to C++. And in Pandas, since version 2.0, you can use Arrow as an optional backend. And since version 3, I don't know when it will be arriving, but there they plan to replace their own string implementation to use the strings from the Apache Arrow library. So then it will be also required for Pandas. And typecasters for arrow types are available as Nanobind extension libraries. And then once you load it, you simply can pass arrow arrays, which is quite nice. So basically, there's this Nanobind Arrow extension library, which has all the inputs in the similar structure like Apache Arrow stores its headers. So you need one Arrow import, which you have to call once as a static module. This is called when you load Arrow in C++, you have to do some kind of static initialization to load the library once correctly. And once this is set up, you can then simply bind your function, which takes a shared pointer of a double array. And then you simply can work with this arrow functionality or access the data. But this is quite nice. You can pass then a huge data just with one function binding in this whole, it could be a double array or a table or whatever you like, and you can simply pass it over in the C++ world without much of a conversion. I mean, you just convert basically the wrapper type because the Apache Arrow implementation in Python is called Arrow, which basically also only wraps the underlying implementation, and this you just change the wrapping, which is no effort, and then you can work with it, which is really nice. All right. Any questions so far? All right. Then, then building. I mean, building is, of course, complicated because, yeah, you have a lot. You have to set up Python, you have to set up your C++, you have to add basically the Nanobind things you need, and you also need, when you do a Python package with C++ extensions, you need to tell somehow Python how to build these C++ extensions. And one way to do it is there is this scikit build core, which is basically a build backend for Python, which supports natively CMake, which is quite cool, and I can show you then if I think time allows in the end in a demo. It's quite nice. But there is another thing. So when you usually want to share your extension as a Python package somewhere, typical approach for extension libraries is the binary wheel format. Because this is quite handy because the consumers of this package then can simply install it from some package mirror. Conversely, when you just distribute it as source, it's really difficult because every user needs a development setup which can compile all the C++ stuff. But there is a problem. When you compile a shared library on one system, it may or may not run on another Linux system, and same is true for Windows and Mac. So this is problematic because since the Python extension uses shared objects, so you cannot compile everything statically, so this is not an option, so it has to be a shared object file. And then you have the problem that it may run on my machine, but not on yours. And to resolve these problems, there is, I mean, the main thing is that if you build it on one system, you always have dependencies on the system C libraries, glibc, for example. And the problem is when you use a recent or Linux distribution like Ubuntu, they always have quite new glibcs, and then you compile it. And if you, I don't know, but the code which is generated out of your whole extensions may use some glibc feature which is only available in a newer version. And then you go to an old Linux system which has an older version of glibc, and then it simply will not work because you have errors in your glibc runtime. And for that, they come up with manylinux. This is basically, they tried to invent a standard to make it possible to build Python extensions that they can somehow guarantee that it's running on another distribution or Linux version with a decent glibc. And you often see in wheels that they have some kind of manylinux _x_y tag. And if you see this, this basically means that the wheel produced will run on every Linux distribution based on glibc version x.y or newer. Okay? And now the question is how you can create this, because if you are limited on a, I don't know, Ubuntu system, you cannot even produce something for old. It's not easy to install old glibc on a running system, so. Correct, there are containers for this, yes. So basically there are, no, okay, yes. Was there, so now I can.
Just says Docker image.
Yes. It is, but I don't, here it is, yes, perfect, it's here it is. Yes. So basically, sorry? Okay.
It gets replaced more. And the Docker image, the Docker registry, the runtime, they are standardized under the Open Domain Initiative, OCI. So OCI image is actually not the term.
Okay. Okay, but currently I think many Linux are still providing Docker images, and so the idea is they use quite Linux distributions which are known for having quite an old glibc versions like Red Hat or Alma Linux, and then they install modern compilers on it, and then the idea is when you build your Python extension on this system, it's guaranteed to run on all Linux systems with at least this glibc version. And there is also another problem when your library or your Python extension requires other dependencies. For example, Arrow, when we install it, or Open Plus, or any other custom C++ lib. They may or may not be present on the system of the user consuming your library or your Python package. And or even if they are present, they may be present in incompatible versions. So the idea is that when you create a binary wheel of your extension, you should also include these dependency libraries in your wheel. And this is also a rather complicated step, but luckily there is a tool called auditwheel, which basically does the job for you. So it can scan your library, your extension on what libraries it depends, and then packages with it. And even better, there is a tool which does everything for you, cross-plattform. I mean, I only tried it out on Linux, but they claim it works also for Mac OS and Windows. And this does the whole building process for you. You can configure it in, for example, a PyProject TOML file, and then you say simply, okay, here's a typo, Python cibuildwheel, and then it generates, it automatically downloads the correct images where you want to build in. Basically, you can specify which manylinux image you want. It downloads it, it compiles a wheel, it tries afterwards that you can install it, and afterwards it's even run all your Python tests on it, which is quite convenient. And then as an artifact, you simply get this wheel file. You can upload to your PyP or whatever mirror you have, and then can simply install it. And this already calls also this audit wheel. And there they, in your extension, they put in all these dependent libraries you say, or they detect, and then they adjust the RPath settings such that when the library is loaded, they are loaded from your package, these dependencies, which is quite nice. All right, then I added a few links in this documentation and also a complete example project where you can also find the documentation. This example project shows how to use Nanobind with CMake, scikit build core, and how to use it with Apache Arrow. Also an example how you can integrate speedlog to the Python logging infrastructure. So basically when you have a C++ library which uses speedlog, then you can simply direct it into the Python logging stream you have in the Python module. And also how to create wheels in the CI using cibuildwheel. And since we still have time, it's also, I will start with a demo, unless there are no questions. All right, then just give me a second. I need to check how I can trick the screens. So I simply will duplicate it. All right, can you see it, or should I make it larger? I guess a bit larger, huh? Is it okay like this? Perfect. Okay. So basically, this is the whole project where the link is in the documentation. I guess we can share it afterwards. It's Nanobind example on my GitHub space. And it's basically set up for VS Code, but it should work just anywhere else. But there is, for the people you knowing VS Code, there are just a few tasks which help you setting it up, installing, it's also documented, installing the required pattern packages for building it, etc. Uses also Conan as a package manager, so it's quite a lot, but I will not focus on it now. So basically, it has, where is it? So I have in my source folder my CPP library, and this has some calculation function which sums up a double numeric vector, which is not that interesting. I mean, the implementation is quite obvious to use accumulate. And then there is a lot of CMake examples. I think people familiar with CMake don't have too much issues to get into it. I won't go now through it. Basically, when you include the Nanobind project, this project also has a, maybe this is interesting, script called find by arrow, and Nanobind is even automatically found. This is quite nice. And then we can go straight ahead to the bindings. Oops, oh, where is it? Bindings. So this is like I showed previously, basically in the example, it just has a few things. Here is the setting up the speed log thing. So basically you have one line where you instantiate a static logger in your module, and then all speed log things are redirected. Then you can add pattern, bindings, documentation. Then what I also didn't mention, you can also introduce named parameters for your pattern bindings when you basically add this _a afterwards in your definition. So if you want a pattern function that can be called with extensions, you can also do it. Here's an example on how you could simply pass in a lambda. So basically nothing new added here. And then regarding the building of this process, we basically have a look at the PyProject Toml setup. There you just specify as a build backend the scikit build core. Then you can enter dependencies as always. And then you have a few build options, how it's packaged. And you can also configure the cibuildwheel, for which pattern versions the wheel should be created, or which Docker image it should be used, etc. Okay? So this you all have here. And then once you have set up everything, you can simply do a so-called editable install, and then it installs all the pattern dependencies. Oh, come on, it's always the same. Oh no, it worked yesterday. Ah, damn it. Copyright. Copyright? What?
Copyright to this.
Okay, damn it. Failed to build installable wheel for some PyProject. Okay.
Further up is another error.
Sorry?
Further up.
Oh.
Yeah, there it was.
Ah, okay. It still requires some. Okay, I know, some internet connection. Yes, it's an internet connection thing, which is
same for me.
Okay, but maybe still, since I installed it, what's also quite cool, there is also an easy way to debug your extensions. There are some. How is it called? You can attach. The idea is you start pattern, then before you load the module, you attach your debugger to the pattern session, then you load the module, and then you can debug your pattern session. And in VS Code, there is also an extension for it, which basically does this attaching automatically for you, which is quite nice. So here I wrote some tests. I simply imported the functions you just saw from the bindings side in my test case. And when I run this, and debug it. Yeah, another problem is that I installed the release version. But okay, I can maybe quickly make a. We don't have some internet here, huh? Okay. Okay, no, not anymore, not anymore. So just a second, and let's do this.
You can search for an RJ45 check in MAC address.
No, no, no. I will do it now like this. But even this has no internet. So, and then let's try, it's now working again. No. Maybe I put that still. But no, I have internet. Damn it. Try once more. Yeah, sorry. Yeah, I can try. Yeah, maybe next time.
You are basically showing the experience of a first-time user.
Yeah, but with flawed internet connection, it's always difficult. No, I think it still doesn't have. Yes, I did, but it's not online, I think, still. But here it works. But I don't know, I mean, we can do a hard clean.
Maybe your WSL is not as
Yes.
clear also.
That's correct.
But I have a question while you're trying to figure out Windows issues.
Yes.
So, during the next half hour, where you try to get in the internet with Windows computer, I have a small question. If I remember correctly, when I worked with PowerPoint 11, I had to write the PI, the interface file myself.
Stubs are automatically generated.
No,
This Nanobind. Yes.
Okay, because previously
Setup.
I had to do it manually, because
Yes,
otherwise you can use it in Python, but you don't have any auto completion or any hints or anything.
I have to make it bigger again. So those stubs are automatically generated.
Okay.
That's quite nice from Nanobind. Yeah. And it's built in the CMake setup of Nanobind. You have a function. I can just go away here. When we have a look at this. So basically where it is, you have a function, a CMake function, Nanobind add stub, and then you can configure it where the input and output is, and then it creates the file and put it next to the package, it will be packaged, and you have complete help in the IDE. All right, so now with the new routing, let's try again. Oh, it's still in progress. These issues. Just a sec, let's try to kill it. Okay. Okay, now they're gone, so let's try again. Wrong. Go away. Yeah, nothing happened. Okay, so now he's at least doing something, I hope. But it still seems not to like it. I don't know, sorry.
We see it's not simple.
Yeah, usually with an internet connection, it's usually simple, but I don't know what's going on here. No. And the strange thing is that I can still not just kill it, and because he says it's just in configuration, is in progress. But I don't want to reboot now, so sorry for this. Any other questions? All right.
Well, maybe more questions in the pizzeria if they come. So, Max, thank you very much for your talk.
Thank you for the audience.
Have you considered submitting it for meeting C++?
No.